7 KSI times by 85 KSI to the power of b, which is minus 0.265, so equal to 0.832. So that's just one of them. So KB is going to be equal to, this is just something that's dependent, it's a size factor, so it's just dependent on the diameter. So we know that the diameter is between 0.11 and 2 inches from equation 620 in Shigley's. So we're going to be using this equation, 879 times by d, which is our small d, I believe, which is 1.625 inches, and that's going to be to the power of negative 0.107. And that's equal to 0.834. And so another factor, which is Kc, is the loading factor. So it's 1 if it's bending, 0.85 if it's axial, and 0.59 if it's torsion. So we only have bending, so Kc is just equal to 1. And all the other one is like a temperature factor, which is 1. We're just seeing at room temperature. So we're going to call that Kd, which is equal to Ke, which is a reliability factor. So they never told us anything about that. So we assume the reliability is 50%. So that's also equal to Ke, and then which is also equal to Kf, which is a miscellaneous sort of environment factor, which isn't very defined. So we now have our Se, which is equal to Ka times Kb times Kc times Kd times Ke times Kf times Se prime, which is our unmodified endurance limit. So that's going to be just equal to Ka times Kb times, all the other ones are 1 times K times by our unmodified endurance limit, which is 42.5, times by our two Marn factors, which is going to be equal to 29.51 KSI. So we can just go ahead and calculate our safety factor here now. So N is just going to be equal to 1, or geez, it's just going to be equal to Se divided by sig A prime, because we know that our sig M prime is 0. So that's just going to be equal to 29.51 divided by, ooh, nice big number there, 63.37, which is obviously lower than 1, so it's not going to have an infinite life. So now, since we know that it's not going to have an infinite fatigue life, we have to calculate how many cycles it's going to take for this to fatigue. So we have to go back to our equation we used in the first problem, which is this one, SF. We actually never used this because we were actually using a low cycle fatigue life. This is N, number of cycles. So it does look close to the similar, or to the first problem, but our A and B are completely different. So A is equal to F times SUT squared divided by SE. So this is our completely modified endurance limit. So this is just going to be equal to, what did we calculate? Did we calculate F yet? Regardless, I guess we can now. So 85 KSI from figure 618 gives an F of, let's say 0.8, 0.87 times by 85 KSI squared divided by 29.51 KSI for our endurance. So that's going to be equal to 185.31 KSI, and we have our B which is equal to the negative 1 divided by 3 times by log of f times SUT divided by SE, which is, you can just calculate that pretty easily. Log of 0.87 times by E5 divided by 29.51. And that gives negative 0.132, or I should say just 133, rounded up. So if we rearrange to figure out, so we assume this SF is, we're gonna use our sigma A instead and plug that into here, and we're gonna pretend that here our yield, our fatigue strength is the same as our yield, and we're going to calculate how many cycles it's going to take to make it fail with this. So let's make some more space down here, and so let's rearrange for n. N is equal to SF over A, and this is going to be to the power of 1 divided by B. Actually, have the brackets in there. So that's just going to be, what do we calculate? For sigma to be before, we had 63.37. So 63.37 divided by 185.31 to the power of 1 divided by negative 0.133. So that is going to give us 3,191 cycles. So that's when it's going to fail. That's how many cycles it's going to take for this thing to fatigue. So that's the majority of the questions answered in the problem. We also have to check for yielding though. So let's just go back to what we had before. Our nominal stress, which is 35.01. So for yielding, we want to actually calculate the maximum stress, compare that to our yield stress. So we're not going to use KF because this is for fatigue. We're going to use this for actual yielding. So let's times this by our nominal alternating sigma stress here, and cut that with SY. So we have 35.01. Going to calculate our yield safety factor, so it's going to be N, it's again going to be SY divided by our KT times by our sig nom A, or sigma A nom, your choice. So our SY, I don't think we actually wrote that down, but in the back of the book here for this again, what kind of steel did we have? We had 1040 cold drawn. So 71 KSI is our yield strength. So it's going to be 71 divided by 35.01, and our KT, sorry, I think our KT was 2.05, I think. Can't really see it from above. So let's bring that over. So as we can see, it looks like we're going to go over 0.989. So this actually means that we're going to yield first cycle, right? I mean, our maximum stress is this, which is greater than our yield stress. On our very first turn, before we even turn it, this is what it's going to fail with. Alright guys, well thanks for watching my video. I hope you learned something. You know, it was a little bit rough, but I don't really have the right tools to be explaining all this you know, the best way that I actually could. And of course the second problem was a pretty big problem, and it usually takes a lot of time by hand. So yeah, if you have any questions or comments, leave them in the comments below, and I'll try to answer them. Anyways, thanks for watching.